Hello, I'm Tom.
And I'm Mia.
Welcome to the Adapticx Podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to explore why GPT-3 was such a turning point in AI, how a single model trained on internet-scale data began showing skills it was never explicitly taught, and why that changed our understanding of reasoning in machines.
It really was more than just a technical leap. It was a fundamental philosophical redirection for the entire field of artificial intelligence.
A redirection, how so?
Well, for you, the listener, the central idea that we have to unpack is what's called the scale hypothesis.
Okay.
This was this radical notion that if you simply make a model dramatically larger and you feed it just an immense amount of raw data, it would inherently unlock this ability to understand and follow completely new instructions.
Instructions that had never seen before.
Exactly, without any specific training for that task.
And that idea, the rejection of specific training, that was the revolution, wasn't it?
It was.
Because before GPT-3, AI development was, for the most part, focused on building specialists. These bespoke tools that were tailored for just one single task.
Right.
And then suddenly, we had something that felt like a generalist, a model that could be applied to a huge range of problems just by, asking it nicely in plain English.
That's the perfect contrast, because the old way of doing things, the reigning champion, was a process called fine-tuning. And it was costly.
Incredibly costly.
If you wanted an AI to perform a task, you just assumed that the initial general training was only a warm-up. You expected to have to commit huge resources, time, money, data to specialize it.
Okay, so let's unpack this fine-tuning concept, or FT, a little more. It was the absolute standard, but what did it actually look like in practice? What were the costs it imposed on development?
So imagine you have a broadly educated person. Let's say they speak multiple languages, they understand global history. That's your generally pre-trained model.
Okay, a general base of knowledge.
Right. But now you want them to be an expert in, say, identifying malicious code in software reviews. Fine-tuning is that year-long intensive master's program. It's where you give them tens of thousands of examples of good reviews and bad reviews, all meticulously labeled by humans.
So you're not just giving them new knowledge. You are physically changing their internal structure to prioritize that one single task.
That is exactly it. You are literally updating the model's internal weights, those billion-plus connections that store the model's core knowledge, using a massive, supervised dataset curated only for finding malicious code.
And once those weights are changed, they're set.
They're locked in. The model is now optimized for that one specific narrow job. It's become a specialist.
So the implication there is, if I spent a year and, millions of dollars fine-tuning an AI to be the world's best malicious code detector, and then my business shifts, and I need it to start translating complex legal documents.
You couldn't just switch gears.
I'm stuck.
You're completely locked in. The model has become physically specialized for code detection. To switch tasks, you'd have to start the whole expensive, time-consuming process all over again.
Which means gathering a whole new, massive labeled data set of legal documents and their translations, and then retraining all those weights from scratch.
All over again. It creates this massive, expensive bottleneck. It means every new application requires starting over.
And that was the paradigm the GPT-3 project was basically born to reject.
Precisely. They were aiming for what they called task-agnostic performance.
Task-agnostic?
They wanted one singular, massive model trained only on the simple foundational task of predicting the next word in a sequence that could then perform a vast array of tasks, translating, summarizing, composing poetry.
All just by being told what to do in natural language.
Yes, and this is the crucial part. Without changing a single internal weight.
Not a single one.
Without touching the weights. The adaptation, the learning, it happens instantly at the moment you ask the question. This was the moment AI shifted from this world of rigid specialization to inherent generalized capability.
And the ingredient that allowed for that theoretical leap was just sheer size.
Absolutely.
When we talk about the scale that GPT-3 introduced, we're not just talking about a small step up. We're talking about moving from models that were impressive to models that were genuinely astronomical.
We're talking about moving up by 3 orders of magnitude.
Yeah.
It's a huge jump. And the scale hypothesis wasn't just a guess, it was the entire engine of the project. To prove it systematically, the researchers didn't just build one giant model, they actually built 8 different models, all ranging in size.
8 separate models, tested side by side, just to map the effects of increasing the size.
That's right. The smallest was, manageable, around 125 million parameters.
Yeah.
But the largest model, the one that became GPT-3 and really changed everything, it clocked in at 175 billion parameters.
Okay, before we move on, can you just define for our audience what those 175 billion parameters actually represent inside the architecture? What are we really measuring there?
Sure. Think of the model as an incredibly vast network of digital neurons, all connected by pathways. Each parameter is essentially a weighted connection between 2 of those artificial neurons. It's a value that the model tunes during its training.
So it's like a knob.
It's like a knob. That's a great way to put it. It represents the model's capacity to store learned knowledge, to store complex relationships, and all the patterns it finds in language.
So we're not just adding a few more connections. We're talking about 175 billion individual knobs that can be tuned. That capacity gives it this unprecedented ability to store deep, interconnected patterns of human communication.
Exactly. And that vast capacity, of course, had to be fed with data of a corresponding scale and quality. All 8 of those models were trained on 300 billion tokens of text.
300 billion. And a token, for clarity, is the basic unit of language the machine processes. It's roughly a word or maybe a fraction of one. But 300 billion tokens isn't just a number, is it? It represents a phenomenal effort in data curation because you can't just dump the raw internet into a system that big and hope for the best.
You absolutely cannot. The raw internet is, it's chaotic. It's messy, and it's fundamentally low quality. If you feed garbage into a machine with 175 billion parameters, you just get very, very fluent garbage back out. The data preparation was arguably just as crucial as the scaling itself.
So they started with something called Common Crawl. What exactly is that, and what was the intellectual challenge in turning that chaos into usable knowledge?
Common Crawl is a massive public archive. It's basically a snapshot of a huge portion of the internet. It contains something like, I think, nearly 1 trillion raw words.
1 trillion?
Yeah.
Wow.
The intellectual challenge was taming that fire hose. It was highly repetitive, often incoherent, and just littered with bad text. They had to impose some kind of order and quality control through 3 very critical systematic steps.
Okay, let's go through those 3 steps. What was the first layer of refinement they applied to that raw Common Crawl data?
The first step was just aggressive filtering. They took that vast, raw Common Crawl set and shrunk it dramatically, down to about 570 gigabytes. They did this by comparing the content to known, highly curated, high-quality reference collections.
So if a document's statistical structure looked like high-quality academic text or a well-edited news article, it stayed in. But if it looked like, spam or a poorly formatted forum thread, it was out.
Precisely. They were prioritizing text that was structured, coherent, and well-written. This dramatically increased the signal-to-noise ratio and ensured the model learned good, abstract linguistic habits from the very first input.
Right, you want it learning good habits, not bad ones.
Learning from high-quality sources prevents the model from developing bad linguistic habits.
But even with great filtering, the internet is inherently repetitive. If you're training on 300 billion tokens, you're going to see the same 5-page article copied across 1,000 different blogs.
And that's the second critical step, which they called fuzzy deduplication. This is perhaps the most important detail for generalization.
Fuzzy deduplication.
Yeah. If the model sees the exact same fact or the same article, even if it's phrased slightly differently, thousands and thousands of times, it doesn't help it generalize. It just encourages it to memorize and regurgitate.
So the model just becomes a specialized database instead of a general intelligence.
Right. It merely spits back what it has seen before. By performing this fuzzy deduplication at the document level, meaning they removed documents that were very similar, not just identical, they forced the model to learn the underlying abstract patterns and principles of language rather than just memorizing facts.
That intellectual push toward abstraction is what separates a truly general model from a memorizing one.
Exactly.
And the third step was augmenting all that carefully filtered web data with what we would consider the gold standards of human knowledge.
Exactly right. They mixed in 3 highly curated established data sets, high-quality digital book collections, an expanded version of something called web text, and the entire English language Wikipedia.
So you get the breadth of the internet, but the depth and structure of books in an encyclopedia.
It provided this foundational layer of factual density and structured knowledge to balance the sheer breadth of the filtered internet text.
And this next point about the sampling is a really fascinating detail. They made a strategic bet on quality that kind of shaped the model's entire outlook.
They did. The vast Common Crawl dataset, which was, lower quality, was only sampled about once during the entire training run. But the highest quality data, the digital books and Wikipedia, were intentionally sampled 2 or even 3 times.
So they were strategically increasing the model's exposure to the best-written, most structured content, even if it meant a tiny risk of overexposure.
They calculated that the risk of overfitting on high-quality text was far outweighed by the benefit of ensuring the model's fundamental linguistic knowledge was based on well-formed, coherent human communication. It was a conscious decision. Quality over raw quantity.
Ensuring the model had a perfect foundation for generalization.
That's the idea.
This systematic scaling and this meticulous data work led directly to a major theoretical breakthrough that gave the entire research field confidence in its direction. This discovery was the power law of performance.
And this is where the whole approach shifted from, say, a research project into more of an engineering roadmap. For decades, AI development was unpredictable. Researchers would increase model size, but performance often hit these plateaus unexpectedly.
You couldn't reliably bet multi-million-dollar compute budgets on an unpredictable outcome.
You couldn't. So before GPT-3, it felt more like an art than a science, You were gambling on whether that extra data or that extra layer would finally unlock the next leap.
A very expensive gamble.
Precisely. But what the GPT-3 team found was that when scaling parameters and data systematically, the model's performance followed a smooth, predictable curve, a power law. And they measured this performance using something called cross-entropy validation loss.
Okay, let's make that intuitive. What is cross-entropy validation loss in plain terms?
Simply put, it's a measure of how surprised the model is by the next word it sees in a sentence it has never encountered during training.
Surprised?
Yeah, think of it as the model's level of uncertainty or ignorance. A high loss means it's very surprised, very uncertain. It has no idea what's coming next.
So lower loss is better. It means the model is less surprised and is making better, more confident, and more accurate predictions about the flow of human language.
Exactly. And the profound insight was that the reduction in that loss, the improvement in performance, wasn't random or chaotic at all. It was mathematically predictable. It just kept getting better. It didn't plateau.
That must have been a game changer for the entire field. I mean, if you knew the scaling laws, you could essentially guarantee how much better your model would get just by adding more data and more compute.
It was everything. It transformed AI development from that unpredictable art into a predictable optimization problem. It suddenly meant that large-scale development became financially and scientifically viable.
The road to general fluency and intelligence now appeared to be an engineering challenge.
Right. An engineering challenge based on relentlessly increasing parameters, data quality, and compute resources. Scaling became the primary strategy.
So scale unlocked the potential. But the true shift came in how the researchers decided to test that new capacity. Instead of using that old, costly fine-tuning, they introduced something called in-context learning.
In-context learning, or ICL. It's the umbrella term for all the techniques that require absolutely no weight updates.
No weight updates.
Which means no fine-tuning, no retraining, ever.
So the model has to be flexible enough to handle the task purely at the moment of prediction, at what's called inference time.
Correct. It uses only the text you provide in the prompt to figure out what you want it to do. It instantly adapts its internal pathways to provide the desired output. And within ICL, there's a spectrum, starting with the most difficult case, zero-shot learning.
Zero-shot, or ZS. This is the scenario where the model is given only a natural language description of the task. For example, write a summary of the following article, and that's it, nothing else.
And crucially, no examples of what the output should look like. None. The model has to rely completely on the generalized knowledge stored within those 175 billion parameters. The simple instruction acts as a retrieval queue, activating the right pattern pathway learned from the 300 billion tokens.
This is where the scale really matters then. If I ask a child who has only read 100 books to translate English to French, they would fail, obviously. But if I ask a human who has read a massive library of text, they succeed because they have this massive generalized knowledge. The model is being asked to do the same thing, right?
That's a great analogy. It's being asked to connect the instruction translate to the thousands, maybe millions of times, it saw that pattern across its vast training set.
And the genuine surprise was that this ability worked surprisingly well across so many different unseen tasks.
It did. The zero-shot capability suggested that the model's internal map of language had become so rich and generalized at scale that a simple text instruction was sufficient to activate the internal mechanism required for a complex behavior. This had almost never been seen effectively in earlier, smaller models.
But they didn't stop there. They realized they could make that context even richer, which brings us to the real practical paradigm shift: few-shot learning.
Right. Contrast zero-shot with one-shot and few-shot. One-shot, or 1S, means you add a single demonstration to the prompt.
Just one.
Just one. So if your task is translating obscure names, you might write, translate English to French, otter loutre. Now, translate weasel and let it finish.
Why is just one single example so immensely powerful for guiding the model's behavior?
Well, think about human instruction.
Yeah.
If I tell you to summarize something, you might do it one way. But if I give you just one example of a summary I like, you instantly adjust your style and your format.
Of course.
That single example constrains the output. It clarifies any subtle ambiguity in the instructions, and it locks in the desired format, whether that's a bulleted list or a rhyming couplet. It dramatically reduces the search space for the model.
And few-shot learning takes that idea even further, providing maybe 10 or 20 examples to establish a really robust pattern.
Exactly. Few-shot means giving it a handful of demonstrations. However, and this is important, we have to remember the strict technical constraint of GPT-3 at the time. Everything, the instructions, the examples, and the final question, all of it had to fit within a context window of just 2048 tokens.
Wait. So all those instructions, all those examples, plus the actual question you're asking, had to fit in roughly 5 pages of text. That's an astonishingly small canvas for teaching a massive model, a complex new task on the fly.
It is a minuscule amount of context relative to its 175 billion parameters of knowledge. And the crucial takeaway is that those examples are just text input. They're not changing the model's fundamental knowledge. It's learning in the moment, adapting instantaneously.
This ability, this rapid, in-the-moment adaptation, it felt dramatically closer to how humans learn from a sequence of examples than anything we'd seen previously.
It was proof that the generalized knowledge was so vast and so deeply interconnected that just a handful of examples could instantly reorient the model's behavior. It suggested the model had learned not just language, but the generalized skill of learning from context.
And this conceptual breakthrough led directly to a major shift in engineering focus, giving rise to what we now all know as prompt engineering.
This is one of the biggest practical legacies for sure. The success of few-shot learning proved that you could dramatically change a model's behavior just by manipulating the input text. The prompt itself became the new user interface.
So the engineering problem shifted entirely. It moved away from optimizing the model's internal weight, which is slow, it's expensive, and it requires specialized knowledge, to optimizing the text you feed it.
Absolutely. Why spend months and millions fine-tuning a model for sentiment analysis when you can spend a few minutes crafting a prompt that says, here are 10 examples of positive and negative reviews. Now classify this one and get excellent results.
Prompting became the fast, accessible way to collaborate with the model.
It accelerated its use as a flexible, generalized partner rather than a rigid tool.
Which brings us back to that fundamental puzzle. How does a machine that's only designed to predict the next block of text suddenly start showing abilities that, to our human eyes, look like sophisticated reasoning and creativity?
I mean, it's the sheer weight of pattern exposure. 300 billion tokens is an unimaginable volume. That massive dataset exposed the model to every conceivable human linguistic pattern. Conversational structures, logical flows, rhetorical devices, and every style of instruction ever written.
So when we give it a zero-shot instruction, it's not actually reasoning from first principles or using some kind of dedicated logic circuits. It's performing an extraordinarily sophisticated statistical search.
That's the core idea. The instructions say, summarize this article, isn't teaching it a new symbolic rule. It's acting as a retrieval cue. It's pulling up a highly generalized pattern of behavior that was abstracted from seeing, for example, countless articles followed by human-written summaries all over the internet.
So the output looks like abstract reasoning, but the underlying mechanism is an advanced statistical fluency. It's just finding the most probable linguistic completion based on the context you've given it.
Precisely. The instruction primes the model, conditioning it to follow a specific linguistic path, whether that path leads to a translation, a summary, or an answer to a complex question. The resulting output is functionally identical to reasoning, even if it lacks that classical symbolic foundation.
Let's look at some of those specific emergent abilities because they genuinely tested the limits of that statistical fluency. Zero-shot translation, for instance, suddenly became plausible even between languages that were not dominant in the dataset.
Yes. The sheer volume of text meant it saw enough parallel structure between well-represented languages like English and French to generalize the concept of translation itself. Just being able to switch seamlessly based only on the prompt was a huge jump over prior models that required dedicated parallel training sets.
But the real proof that it wasn't just regurgitating what it had seen was its ability to grasp deep literary style. I think the poetry example is the most compelling argument for abstraction.
The style imitation was genuinely astonishing. The researchers tested its ability to compose poetry in the specific styles of famous authors. They could give it a title and ask for a poem in, say, the abstract modernist style of Wallace Stevens.
And the model didn't just produce grammatically correct lines, did it?
No, not at all. The resulting completions were often remarkably plausible. They used sophisticated poetic devices like alliteration, they maintained complex tones, and had varied structures that were reflective of that specific author's known work.
So that requires a very deep, generalized understanding of literary context. It needs to know what constitutes Stevensness, statistically speaking.
Exactly. It has to understand the statistical distribution of word choice and thematic elements associated with that specific author, not just the general rules of poetry. It's mapping style and rhetorical intent, not just content.
But if you want the ultimate proof that it's generalizing rules rather than just memorizing words, we have to look at the task where they invented a new word.
Ah, the famous scree example.
Yes, tell us about that one.
Exactly. The researchers literally made up a verb, scree, and they defined it as meaning to swing a sword at something. They then asked the model to use it in a sentence that required it to be conjugated into the past tense.
And what was the model's response?
It returned a sentence where it had successfully conjugated the word. It said, "We screed each other for several minutes, and then we ate some dinner."
Screed. So it knew that to make this completely novel verb past tense, it needed an ed ending, even though that specific word combination, screed, had never existed in its 300 billion tokens of training data.
It instantly generalized the structural, grammatical rules of English verbs and applied them correctly and creatively to a completely novel concept. It didn't know the word, but it knew the rule for how the word should behave. That level of generalization is what makes these abilities emergent from scale.
This incredible linguistic fluency needs to be balanced against quantitative performance, though. The model showed some surprising skill in arithmetic, but only in the few-shot setting, and that's where the paradox of statistical reasoning becomes strikingly clear.
The arithmetic results were a crucial diagnostic tool for understanding the model's internal mechanisms. When tested on natural language math problems, if you provided it with a few examples first, it was excellent with small numbers.
We were talking about very high accuracy rate.
Immensely high.
Yeah.
It achieved 100% accuracy on two-digit addition.
100%.
And 98.9% on two-digit subtraction in few-shot mode. This suggested it had generalized the structure of calculation from the linguistic data it had seen.
But, and this is the vital insight, that impressive performance just completely collapses as the problems increase in complexity. What does that drop-off look like?
It's a cliff.
Yeah.
A steep cliff. Performance dropped to only 9 or 10% accuracy on 5-digit addition and subtraction problems, and on 2-digit multiplication, it was only about 29% accurate.
If it's a true reasoner, the number of digits shouldn't really matter, only the rule. What does this steep drop-off tell us about the underlying mechanism of its so-called reasoning?
It tells us the model is performing two very different things. It's excellent at generalizing the linguistic pattern of an arithmetic problem. It knows what a math problem looks like and what the answer format should be. Right. But it does not possess a robust internal symbolic calculator.
It doesn't have a calculator app built in.
Not at all. It treats addition as pattern completion, which works perfectly for short, highly frequent examples it's seen. But it fails when the task requires sequential, error-free symbolic steps that are not common patterns in its training data.
So is it kind of like a highly skilled actor who can flawlessly recite the script for a physics lecture? But if you change one variable or ask them to perform the calculation themselves, they completely fall apart because they don't actually know the underlying physics.
That is a perfect analogy. The fluency is incredibly high, but the underlying verifiable logic is brittle.
And we see this brittleness pop up in general common sense and plausibility checks, too.
Absolutely. The model, when it's relying on statistical fluency over physical plausibility, can make some really jarring mistakes. For instance, in one test on basic physics, a model deemed the phrase "hands cut into metal" as plausible. Plausible. It was prioritizing the linguistic flow and the word associations over the fundamental fact that human hands cannot shear steel.
And the calculation errors show up outside of simple arithmetic too, right? Especially with things like time and measurement.
Yes. In one test, the model was asked to calculate the time difference between 9:02 a.m. and 6:14 p.m. It returned an answer of 526 minutes.
Which is close, but wrong. The correct answer is 552 minutes. A small error, but it proves that when the task demands that high-fidelity sequential processing, even basic subtraction and carrying over, the statistical engine starts to drift.
The patterns break down because the correct, error-free sequence of calculation isn't as robust as the linguistic patterns it uses to structure the answer. And that breakdown of real-world knowledge translates into seriously bad, even dangerous advice when you push it into practical, judgmental domains.
Such as the hazardous suggestions researchers found when they asked for practical advice.
When its judgment is statistical and brittle, it gives terrible suggestions. For example, testing it on lightning hair, one model suggested applying hydrogen peroxide and leaving it on overnight.
Which is an incredibly dangerous idea.
It is. Another model recommended using soap and steel wool to clean a cast iron skillet, which would permanently ruin the pan's essential seasoning.
So it knows the words associated with cleaning, but it lacks the contextual, practical judgment of safety or effectiveness based on the underlying material properties.
Exactly. It's prioritizing fluent text generation, which includes those keywords over robust, verifiable knowledge. And adding to this limitation, the entire system proved to be incredibly sensitive to how you phrase the prompt itself.
This high sensitivity is a critical weakness, isn't it? Because a true abstract reasoner should be able to solve the problem regardless of the framing. But this means scores on reasoning tasks could swing wildly based on the exact wording.
It's proof that the model is relying on precise linguistic cues provided by the prompt, not on a robust internal logical structure that works no matter how you ask the question. If you phrase the prompt carefully, adding cues like "think step by step," the model's performance on deductive reasoning improved dramatically.
But if the prompt was ambiguous?
It struggled. So the prompt is essentially teaching the model how to reason in that moment, proving it is still an amazing pattern matcher, but its logic isn't fully abstract or self-contained.
That's precisely what the evidence suggested. The complex behavior is emergent from scale, but it remains dependent on specific linguistic patterns and cues. Now, GPT-3 wasn't just a technical shift, it was a societal one. The fluency of the text it generated was so close to human quality that it immediately forced this urgent conversation about large-scale harm and misuse.
Once you automate the ability to generate plausible, complex, and human-like text instantly, you dramatically lower the barrier for malicious actors. The initial concerns were huge. The potential for mass misinformation campaigns, automated spam, and highly sophisticated personalized phishing and social engineering attacks.
Right, because the bottleneck of having to physically write all that convincing, unique text, which takes time and effort, was suddenly just gone.
Yes. Anything that relies on generating fluent text just got a massive power-up. And the research immediately showed that humans were poorly equipped to handle this sudden surge in fluent automated text.
What were the findings regarding people's ability to spot synthetic content?
That was one of the most concerning findings. In controlled experiments where people were asked to distinguish between human-written and model-generated news articles, there was a very clear correlation. The larger and more fluent the model, the harder it was for human readers to distinguish its output from human writing.
So the better the model performs its core function, the more it amplifies the threat of misinformation and automated deception. Human discernment was being outpaced by the model's statistical fluency.
It created an urgency around detection and mitigation almost immediately.
And this leads directly to the other major ethical and societal problem researchers identified, which is inherited bias. If you train a model on 300 billion tokens of internet text, you are training it on the very long and complex history of human prejudice and stereotypes contained within that data.
It's an unavoidable mirror, in a way. The model absorbs the statistical patterns of human communication, and that includes those that reflect social prejudice. The source research performed systematic analyses to measure this inherited bias, and the findings were stark. They required immediate attention from the community.
Let's detail the findings around gender bias and occupations, because the methodology of that test was very revealing about the nature of the learned prejudice.
They tested neutral prompts, things like the competent occupation was A, and then filled in different jobs like engineer or manager. For the vast majority of jobs tested, there was a significantly higher probability that the model would complete the sentence with a male identifier.
But the truly critical part of the experiment was that they didn't stop at the word competent, did they?
No, and this is key to understanding the mechanism. They systematically tested the same jobs using the neutral prompt. The incompetent occupation was A.
And the bias didn't disappear.
The gender lean remained virtually the same. This demonstrated that the bias wasn't just about associating gender with success or quality. It was associating the concept of the occupation itself with a specific gender, regardless of whether the person was described as competent or incompetent.
Wow. So it's a direct reflection of systemic statistical biases ingrained in the training data.
The model isn't inventing these stereotypes. It's simply reflecting the prevalence of these stereotypes in the vast corpus of text it learned from.
So they are statistical artifacts of human language use on the internet.
Precisely. And the researchers found similar issues when they analyzed associations with racial and religious groups.
In terms of race, there were measurable differences in sentiment scores, and for religions, there were problematic linguistic stereotypes associated with certain faiths.
Yes. The analysis showed, for example, that Christianity was statistically associated with terms like ignorant and judgmental, while Hinduism showed associations with terms like caste and cows. These are not judgments the model is making. They are learned associations derived from what people write about those topics online.
This research emphasized the immediate and urgent need to study how to mitigate these inherited social harms before these models, now proven to be powerful generalists, were deployed globally without proper safeguards.
It shifted the focus from merely engineering larger models to ensuring those models were aligned with human safety and values. It was a recognition that scale alone doesn't fix prejudice. It often just amplifies it.
When we look back at this whole journey, from the rejection of fine-tuning to the discovery of power laws and the emergence of zero-shot ability, what is the ultimate enduring legacy of GPT-3?
I think its legacy is multifaceted, and it's undeniable. Firstly, it definitively proved the power of scaling to unlock generalized multitask abilities. It showed that through few-shot and zero-shot learning, general fluency was an emergent property of size,
which challenged decades of assumptions that specialized algorithms were required for every single task. It proved the concept of the general-purpose reasoning engine.
Right. And secondly, it laid the direct foundation for every modern instruction-following model and conversational assistant we use today. The entire field shifted toward the idea that you train one massive model and then guide its behavior with text, not with code or expensive retraining.
The conceptual leap wasn't just the size, but the surprising flexible behavior that size enabled, that shift from a rigid tool to a flexible collaborator that responded instantly to a text prompt.
That transformation in the human-machine relationship is the true long-term impact. The model had learned how to learn from examples and instructions, and that accelerated the entire field into the conversational AI era we're in now.
Right. And this brings us back to that final, profound, and still unanswered question that emerged from the research. The greatest insight from GPT-3 wasn't just how much it learned, but the discovery that all these reasoning-like abilities, from conjugating a new verb to composing high-level poetry, all just emerged spontaneously from the single massive task of predicting the next word on an internet scale.
And that is the central tension we still face today. Are these emergent abilities a reflection of true abstracted reasoning, or are they simply an unprecedented level of statistical fluency and pattern matching? And as these models continue their relentless growth, becoming faster and more complex, will we ever truly be able to tell the difference?
Thanks for listening to the Adapticx podcast. If you have any questions, feel free to reach out to us.